Good afternoon, everyone. It's a little lighter crowd today, but that's okay. I am glad you all came out this afternoon for the third to last of our speaker series for the Human-Centered Design Research Speaker Series this autumn quarter. So it's my pleasure to introduce Dr. Katya Cherukumilli. So Katya joined us just last year in 2023. She came in from UC Berkeley, got her PhD there, but then came and also did a postdoc here at the University of Washington with CoMotion, where she did all sorts of cool stuff on a nonprofit organization related to water filtration systems. And if you come to this series, normally you might notice that we often have like a computing flavor to what we do. And Katya is actually part of HCDE's strategic plan to sort of think about human-centered design beyond just sort of the traditional field which it grew out of computing, and bringing it into other aspects of engineering. And so I'm so pleased to have Katya as a member of our department. I think she brings a really diverse perspective, and so many of the sensibilities around human-centered design apply to so many different problems. And I'm so grateful to have Katya here to talk about her work and water quality. So take it away, Katya.
Hello, can you hear me? Okay. Hi, everyone. My name is Katya Cherukumilli. Thank you for the introduction, Julie. In addition to what Julie already mentioned, I can tell you that I'm also an adjunct faculty in civil and environmental engineering, and also in environmental and occupational health sciences. And I direct a lab here on campus in HCDE called the Safe Water Equity and Longevity Lab, also known as SWELL. A few of my students are here today, and I'm really excited to share with you the work that we've done over the last year. It's very preliminary data. We're still in the phase of data collection. And none of this work is published. So I just want to add that caveat so that you understand that the research I'm going to present to you today is not a finished story yet. It's still ongoing. So to start off, let me tell you a quick update on my lab. We have 3 different research areas, the first one of which I'll focus on a lot today, called Define. Here we're studying how infrastructure impacts how users perceive water safety, what experiences they have, and what behaviors they show towards usage of different water fixtures. We also look at how we can communicate safety risks to users. So here we're working at a lot of different scales. I'll talk about 2 projects in this research area today. One focused on campus infrastructure here on the UW campus. Second one is looking at lead remediation in Washington State schools. And a lot of my prior work, as Julie mentioned, has a global context. I've worked in India, Kenya, Tanzania, but today my talk won't focus on that. Other parts of my lab we won't get into a ton today are thinking about designing solutions to the problems that we define, all the way from experimental studies to user testing in the field, in addition to prototyping. And of course, in thinking about designing solutions, we also have to think about how we deploy them. Who do we partner with? Which stakeholders are important when you're thinking about transferring technical expertise? What is the regulatory and policy context in which these technologies will be used and commercialized? So again, here we think at a lot of different scales, from the individual and household scale all the way to utilities. So to start off, I know not everybody here is kind of a water expert, so I'll give you a quick background on federal regulations around drinking water, just to get you acclimated to the jargon and the things we'll talk about in the talk today. So first off, when we think about drinking water systems at the national scale, there's kind of 2 categories. We have public water systems that are actually regulated by the Environmental Protection Agency, known as EPA, and then we have non-public water systems. So within public water systems, we have community systems. This is probably what most of you in this room are most familiar with. So think about the utilities in our city, like Seattle Public Utilities. These systems are serving the same population year-round. We have non-community water systems, which serve fewer people for a shorter period of time. They can be transient or non-transient. And when we think about community systems here in the public water system category, this also actually includes schools and universities, because we are getting our water from the utilities and the water treatment plants in the city. So we are not considered a non-community system because we don't have our own source. However, there are some universities here in Washington State, in Eastern Washington, where they are actually their own public water system. They might be getting water from a well and so on. So this is kind of an important distinction in how the EPA regulates water. Now, in terms of non-public water systems, well, private wells, so for individual homeowners, these are actually not regulated at all. There's no requirements on testing or treatment, and this is very critical when you think about water safety because a large amount of people use groundwater as their primary source of drinking water, both in the state and country and globally. There's one thing missing here on the map, that a water system we haven't talked about. Can anyone guess what that is? Bottled water. So this is actually not regulated by the EPA at all. It's regulated by the FDA, the Federal Drug Administration. So when we think about how the EPA actually regulates drinking water contaminants, we need to think about three questions that the people are asking themselves. Does the contaminant affect health? Does the contaminant occur frequently in water systems? And could regulating it actually mitigate health risks? If the answer to all three of these questions is yes, then the EPA decides to develop legally enforceable primary drinking water regulations. There's a few different types of primary drinking water regulations that are important. So we have something called maximum contaminant limit goals. So MCLG. These are not enforceable, and they're goals that you recommend that systems try to achieve, and they're solely based on health risks alone. The reason they're not enforceable is because in order for something to be enforceable, you need to also consider the technological and economic feasibility, not just health. So when contaminants have maximum contaminant limits, not all contaminants have these, some do. For example, arsenic has a maximum contaminant limit of 10 parts per billion. This is something that's an enforceable standard that you can go and the EPA can say, hey, water treatment plant or public water system, you're breaking this rule. We need to think about the violation and how you'll address it. The last type of national primary drinking water regulation is called a treatment technique. So this is for particular contaminants where having a compliance with the maximum contaminant limit is a little too costly or difficult. And systems instead are required to treat water above a certain action level. So the treatment technique goes into play if they kind of violate a certain standard. So to give you some examples of all these different types, let's take, for example, lead in drinking water. The maximum contaminant limit goal based on health alone for lead is 0. No amount of lead is okay for you. That's what they say. However, when we look at maximum contaminant limit, this actually doesn't exist for lead in national regulations. Instead, the lead follows the lead and copper rule treatment technique that says, just as of last month, this was reduced to 10 parts per billion. It says if public water systems exceed 10 parts per billion, then they have to take into account corrosion control mechanisms like adding orthophosphate or something that prevents lead dissolution. So what if the answers to these questions are no? Then the EPA actually decides not to develop legally enforceable regulations. Instead, they have other things called health advisories, which are kind of suggestions and guidelines on how people could act based on emergency spills. You might see things like, don't drink the water at this campsite. That's a health advisory. In addition, you have secondary drinking water standards, which are based not on health at all. These are more based on aesthetic or cosmetic concerns. So how does the water taste, or what does it smell like? What does it look like? So some of the most common contaminants, or rather chemicals that you think about that have secondary drinking water standards, are fluoride, aluminum, iron, and zinc. So today I'd like to share with you the first research project we did on the UW campus. We just submitted a paper at CSCW called Safe Drinking Water Provision at Universities is a Shared Responsibility, Not a Kafka Novel. And this part of the title came based on an interview we did. Somebody actually said, at this university, handling drinking water sometimes feels like a Kafka novel. So let's get into it. Here I have some of the people that contributed to this research. It was actually led by a master's student in our department named Jessamine Lee. In addition, we have here in the audience Anton, who was a volunteer from a high school volunteer this summer with my lab, who contributed a ton for data collection. And the project actually started last year with the directed research group in HCDE, many students helping design the survey and implement it. So let's start off by thinking about which university stakeholders actually care about campus water. Let's take, for example, at UW. So there's all of us, Huskies, right? The campus users, the visitors, the people that are coming here. We care about water because we're thirsty and need to drink it. The building coordinators care about it because they're kind of tasked with having to maintain the infrastructure that we all use. Campus facilities care about it because they come in when there's issues and they have their different shops on campus to help fix issues. Environmental health and safety will care about it when the water could pose a health concern. And also they're tasked with dealing with lab safety and other issues beyond water, of course. Department chairs like Julie here and college administrators, deans, and so on will care about it because it has an impact on finances and reputation, as we'll see on the next slide. And of course, university leadership can help guide policy and set things in place that will influence water. So now I want to ask you, why should university stakeholders care about water? The obvious one is health risk, right? We have a lot of people that are on campus that could be exposed to things. But in addition to this and beyond this, we need to think about the reputational risk. What is the public perception of the university? How could this affect recruitment and retention? In addition, there's sometimes a financial risk. Certain departments housed in certain buildings might have to spend more on water. It might affect how their research goes and so on. And a little example of this you can see on a Reddit thread where people are, taking pictures and talking about water and so on. This is something that we want to kind of avoid. So the research questions that we are focused on for this area of research is, how does the type and quality of drinking water fixtures vary between buildings? To what extent is safe water provision something that's collaboratively managed? And how does the infrastructure itself affect what users think and do? So to start off, to answer each of these questions, we had kind of a multi-pronged approach and methodology. First, we did 50 building walkthroughs, conducted an infrastructure survey. We did expert interviews with 9 building managers, and we conducted an online user survey that has to date gotten over 500 responses, and we only submitted it last week. So this is we're continuing to collect the data. So in terms of the infrastructure survey, there's over 300 buildings on the UW campus that have been constructed from over a century ago. You can imagine it's going to be hard for my lab alone to do all this work in this large of a space. So we actually excluded certain buildings from our infrastructure survey analysis, such as museums, libraries, and super specialized buildings. And we chose instead to focus on buildings that had multi-use capacity, where there were undergraduate classrooms and labs and offices and so on, that more people were kind of using rather than a specialized, restricted set of users. So in terms of data collection, we thought about this a lot because we wanted something to be efficient and easy and engage anybody that wanted to interact with this research. So we decided to go with phones and Google Slides. Initially, we had a survey set up, but this was actually much easier. So what we did is on a Google Slides presentation, we kind of had a template of different floors in a building, and we asked people to take pictures of the fixtures that they could find when they're just walking around in the hallways that were publicly accessible. We wanted pictures of the brand and the model, and if there were multiple fixture types, we left room for that, and also this could easily be changed too. So here's an example of the building we're in right now, Johnson Hall. So here you can see all of the water infrastructure that's available in this building, in addition to the serial numbers and manufacturing codes of the fixtures, so that we can later look up and start to think about when was this manufactured, when was this last treated, and so on. So in terms of the results from this 50 building walkthrough survey, which was conducted this summer, we found that the most common drinking water fixtures on campus were metal water fountains, even though they were not all the same. There were about 15 different varieties of fountains that existed. We also found less common, probably the least common, was porcelain water fountains. Some buildings had bottle refill stations, some had water coolers, and some had vending machines. You can see I've color-coded these, meaning this side is public tap water. Okay, so this is what has been plumbed into the building and is being provided by the public water system. On the other side, we call this plastic bottled water or private bottled water, meaning it's totally a separate entity from the building and not impacted by the premise plumbing and so on. So before I get into the details of the infrastructure survey, I wanted to show you a high-level snapshot of what we're learning from our user survey. We haven't analyzed all the results, but we already found something really interesting. When we asked people for every single attribute of drinking water, would you think bottled water exemplifies this or tap water? So it was kind of a battle between these two sources. As you can see, most people in our survey, a vast majority, thought bottled water was higher quality, safer, and tasted better, and they thought tap water was the one that was more affordable and more convenient. So this ties into some approach of tools that we're trying to design to address this issue in terms of the culture of sustainability. So campus has a sustainability plan that by 2025, we want to reduce all waste, including single-use plastics and packaging, by 10%. And our kind of design hypothesis is that maybe plastic waste on campus could be reduced if we highlight the convenience and affordability of public tap water, while at the same time encouraging infrastructural upgrades with informative signage that can kind of both improve the taste and quality and also give people a stronger sense of safety so that they can trust and know what the water they're drinking is. So now let's get into the first data set of looking at what the water fixtures are. And here we're plotting the fixture type and the count of fixtures in each building by the year the building was constructed. One thing the graph I'm going to show you doesn't take into account is when a building was remodeled, because that data was so difficult to find. So we just stuck with plotting when the buildings were originally constructed. So here you can see of the buildings that were built all the way from 1895 to present day. It kind of goes on, we have our newest building that's the interdisciplinary engineering building built next year. You can kind of see a little bit of a trend in what's going on, but at the same time, the main takeaway is that across buildings, metal water fountains are the most common, but most buildings have multiple type of fixtures. It's not just one thing that they need to maintain. There's a lot of variety. Some interesting things I saw were that porcelain fountains were more found in mid-century, early 1900 type of buildings. We saw bottle refill stations, the most like sustainable and upgraded ones, all throughout. So this is kind of an indicator. For example, the building that was built over a century ago having a bottle refill station indicates that it's been remodeled and become a part of the remodeling effort. So if we're now plotting the building construction year against the fixture manufacturing year, first thing to notice is that we don't actually have information of all the fixtures we documented on when they were manufactured. This is because when we actually look up the serial numbers, some of them are no longer being manufactured, so they're kind of outdated. Some of them might be on recall lists. Some of them are just no longer, they might be old enough that they don't have information about. So for example, you can see that only one porcelain fountain is on our graph because these are not things that came with serial and model numbers etched into the porcelain. One thing I want to draw your attention to is that in 2014, the EPA passed the Lead-Free Plumbing Act, where it restricted lead in plumbing fixtures, solder, flux, anything that's involved with building pipes and using pipes. It restricted it to 0.25% or less. So this can kind of give us a sense of how to triage and figure out where we need to focus our efforts on if we do future water quality testing. I'll go over this part quickly because I have a lot of results I'd love to share with you, but when we interviewed the building coordinators, we asked them a few different things about stakeholder roles and responsibilities. One of the most interesting things we learned through the survey is that building coordinator roles are actually unpaid most of the time, voluntary, not well defined, and they actually don't receive formal training. So this is an area where we could intervene to add modules related to water safety and so on so that people can all be up to speed. In addition, when we asked about challenges related to water management workflow, there was inconsistency in which buildings replaced their own filters versus if somebody else did it. And so there's something we can do here to help increase the transparency and communication between all these different stakeholders I was talking about earlier. In addition, some repairs were considered urgent, like for example, if there was a leak or something smelled bad, but other more routine repairs, such as replacing filters regularly, is not as urgent and it's kind of deprioritized. In terms of the motivations and barriers, when we ask people, when do you decide as a building if you're going to upgrade infrastructure? A lot of the building coordinators said that they wanted to increase user satisfaction, they thought it would improve water safety and so on, but the barriers they felt were primarily cost prohibitiveness, and there were some approval processes that could be simplified to make this easier. In addition, because there was no training, there was no clarity on whether or not they were responsible for filing these work orders. So there's some level that we can help share amongst buildings that had more advanced and upgraded fixtures and not, where we can help bridge this communication gap. And lastly, in terms of impacts on user experience, building coordinators who really know their user population well noticed that they had a strong preference for certain type of fixtures over others. The users also kind of reduced their complaints overall, and they would avoid certain fixture types in buildings. So in this paper that we submitted to CSCW, one of the tools that we suggested that we could help design, in addition to a campus sustainability fund grant that we're hoping to secure later this year, we can actually implement this idea, is near every fixture, if we had a QR code that anybody could interact with, they could do two things. One, if there was a maintenance issue, they could help report it right then and there, so all of the burden doesn't just fall on one stakeholder to do it, but it's kind of more of a distributed responsibility. Or if they were just curious and they wanted feedback on the water quality or when the filter was last replaced, this QR code could link to a broader database that allows them to get information about the fixture so they can feel more assured and have a sense of security. So to kind of put that into action, the behind the scenes database that kind of QR code thing is going to collect could be displayed on and integrated with the campus sustainability map, which could have information about where the nearest electric vehicle charging is. We could also have a section on bottle refill stations and their status. So where are the green bottles that have recently been maintained? In addition, you can kind of see that if you click in a particular building, we're proposing that you can understand, what the latest water quality test was, when it was replaced, and so on. So this is kind of a way for outside campus visitors to interact with campus sustainability and internal users to help with safe water management. So next steps on this project are, we want to analyze, obviously, this user survey data. We're going to close it close to Christmas break. So by then, I'm not sure, we might have over 600 responses. And we want to basically understand and make connections between how users' perceptions of building water infrastructure might impact their behavior and preferences. I forgot to mention earlier, but the survey is actually customized for every single building. So if you see the survey in this building and you want to take it and you click Johnson Hall, you'll only see the fixtures in this building so that you can respond whether or not you use them and which ones you perceive to be a certain way. As I mentioned, we're going to apply for the Campus Sustainability Fund, and we're going to collaborate with important and critical stakeholders on campus to talk about science communication and how to share these results and what kind of strategy we can take to improve safe water provision. So now I want to shift gears to another project I want to share with you called Lead Contamination of Drinking Water in Washington State Schools. This is also looking at primary schools and childcare facilities in the state. And this project was also very collaborative. I had a REU undergraduate student, actually a freshman at Swarthmore University, that worked with me all summer, Amelia. And we have Angela here in the audience back there. She's an undergrad in CS here at UW. And my PhD student, Stephanie Hung, is also going to work on parts of this project as we move forward. So to give you a little bit of background on this topic of lead policies in the US, as you saw, we need to define what the regulatory context is before we dive in. We need to truly understand what's going on. I decided to make a timeline of the history and the story of lead in the United States and our efforts to phase it out. So it kind of started in 1974 when Congress passed a law called the Safe Drinking Water Act, which basically gave the EPA the power to create regulations like we talked about to monitor and regulate water quality. In 1978, they banned lead in paint. So houses before 1978 might have lead in their walls and the paint, but after that you can be pretty assured that they don't. In 1988, the Lead Contamination Control Act gave CDC kind of the task of monitoring blood lead levels in children, school-age children, and it also banned lead-lined tanks and coolers used for water. Then we had an effort to create lead-free plumbing in 1986, but this only limited lead content to 8%, so it didn't actually make it lead-free. In 1991, we had the lead and copper rule, which was the treatment technique about corrosion control I talked about earlier. Then we banned lead in food cans and gasoline in automobiles. In 2014, they realized, oh shoot, in the 80s we should have banned it and made it lead-free, so they reduced it down to 0.25%. And this is plumbing materials, including solder and flux and pipes. More recently, in the last few years, a lot has happened. The lead-copper rule was revised in 2021. In 2023, an NGO published a Get the Lead Out report, which I'll go over. And then just last month, the lead and copper rule improvements were enacted. So basically, with these recent legislations, this requires all public water systems and utilities to inventory the materials of their distribution lines and to document anywhere where there's a lead service line and put it up publicly. And then within the next 10 years, they need to replace this with some other material. So this is huge. In LCRI, we also have some federal mandates requiring schools to test. This is the first time ever they focus specifically on children and schools and childcare facilities. So you might be wondering, where is lead coming from in your drinking water supply? So this diagram made back in 2012 by some authors shows sources of lead outside of the school in the water distribution system, because when it's coming from the water treatment plant, rarely is there a lead. Lead gets introduced as it moves through the building. So you could potentially have a service connection like a lead pipe or a gooseneck right where you're connecting to the water main underground in the city that could cause it. You could also have galvanized iron pipes, lead solder joints, strainers, the fountain itself, the aerator, the faucet. There's so many areas. As I mentioned in the laws, each of these components was regulated at a different time. However, when the building is built, you can't go back in and remove everything unless you rebuild it, right? So what we need to really think about is, what do we do at the point of use, at the end, after it goes through? How can we protect our children? So as I mentioned earlier, the Get the Lead Out report was published in 2023. And basically, Environment America and a public interest research group collaborated, and they looked at all of the lead policies that every single state had. Because even though there's a federal level policy, it's not very strong for controlling lead. So every state kind of has to make its own regulations. And they went through based on these policies and literally did it like a report card. They had a rubric and they gave every state points based on policies. And you can see Washington State, we have a C+. The states that are beating us out are DC, well, that's not a state, but we have New Hampshire, New Jersey, and then a majority of the states in the country actually have an F, meaning a majority of the states in this country are not setting policies related to lead to protect school children. So why did we get a C+? Why didn't we get an A? Well, let's talk about it. So here on each category, I show you the percentage of the grade we got and where we could have done better. So our action level for schools is actually 5 parts per billion, which is lower than the federal limit of 10. But other states have set it even better to 1 parts per billion. They need to act and have treatment if you're above 1. In terms of remediation, we say let's shut off taps, let's install filters and so on. But other states, they don't care about testing. They're just saying let's replace all fountains, whether or not there's lead, with bottle refill stations or something better. Let's put filters on anything that puts water out because someone might drink it. That's way more progressive. Now, in terms of testing requirements, Washington, they say follow the 3 T's protocol for testing, don't flush it before you take a sample. These things are known to hide lead, and we do require testing regularly, but other states actually do it every year and multiple samples per tap. In terms of public disclosure, we do have an online dashboard. We do disclose when we have solutions, what we do to the public, but other systems also are not afraid to disclose system risks and other sources of lead. We did get 100% on applicability of policy requirements, meaning that all of our state's policies apply to both schools and childcare facilities. So there we're doing well. And this actually says 0 in the Get the Lead Out report, but I just told you that last month, now everybody is federally required to do this. So technically we have 100% here, which means we might have a better grade than a C+ next time they publish this report. So how is Washington State actually trying to address lead in water? Well, you don't have to look at the details of this. This is just the dashboard by the Department of Health. But what I want you to know is that there's tons of testing data. Okay, so we actually know where there's lead, where there's not, in a lot of schools across the state. We also have funding to remediate and address the problem. So why is this still a problem? If the Office of Superintendent Public Instruction is actually offering millions of dollars, why are we still having this gap and this issue? Let me just summarize what you need to apply for this grant. So only school districts can apply. You have to prove that your fixtures are contaminated. You need to use this funding to do anything to remediate. You can replace a fixture, add a filter, or replace a pipe, but you can't use employee labor costs of school district officials. And schools can only replace like for like, meaning if a tap's contaminated, you can only replace it with a tap. You can't just upgrade it. So this is kind of silly because a lot of people will want an upgrade rather than doing a like for like. So just to show you how much this funding has been unused, I collected data by talking to the grant program manager and found out every biennium, so every 2 years, the OSPI will ask the state for money from the capital budget, and you can say any value. I could say, I want $3 billion, okay, maybe not $3 billion, $2 million, and the state will say, okay, we appropriate this funding for remediation of lead. If at the end of those 2 years, every biennium, that money is not used, it gets sucked back up into the state, so basically wasted. So what you can see, in 2019, we asked for $1 million, got $1 million, $750 went back. Next biennium, we asked for $3.47 million, got it, only had to return $3 million back. This is explained by COVID. You can see very few districts applied for funding for remediation, and I think COVID plays a large role, but we can't use that COVID excuse anymore in this last and current biennium where we had a $1.5 million available and still $500K is remaining unused. So this is a really big concern that my lab is trying to understand. Also, if you look at the details, some school districts are applying for hundreds of dollars, whereas some are applying for $1 million. What's up with that? So there's some issues with how this grant is being managed. I'm not gonna go over all this, but this is kind of the information that schools are being asked to submit. And I actually asked the grant program manager, can I look at the interface of what a school district official might do? And they showed me, and I took a screenshot. Oh no, my animation's not working. I'll show you later. It's very drag and drop. You do line by line. You have to say 4 fixtures in this school of this age had this thing. It's incredibly time consuming. So this brings me to my point of what can we as engineers and scientists and designers and researchers and people in this room actually do to address this issue? Well, I'm a professor, so I do research. So here are some research questions. Working with some of the data sets that I'll show you, we wanted to understand how a child's lead exposure is impacted by where they live, where they play, where they go to school. We also wanted to understand, are there relationships between student demographics like race and income level of their household, where the school district they actually are a part of is, and how much contamination they're exposed to. And then we also had a more qualitative research aim of understanding the barriers and motivations that school districts have to seek funding and actually implement it. So for this research project, we had the methodology of first aggregating data from disparate sources, including the Department of Health, OSPI, and the Washington Geospatial Open Data Portal that has a lot of boundary maps that you can use to plot data. We did a lot of data visualization with the aggregated data to map high priority, high risk areas. And we're going to conduct more expert interviews with school district officials. I love this little cartoon because it makes it seem so glamorous, even though it's just a Zoom call and we don't have a red carpet. Okay, so the first graph I'm going to show you from this data is how we think we can help school districts apply for this funding. We decided to go and estimate how much it would cost to replace all of the contaminated water fixtures in a school. So when I say the word contaminated in Washington state, according to law, what we mean is greater than 5 parts per billion lead. If a fixture reports that as the result when you take a water sample, then you can apply for funding for that particular fixture. So these are the different fixtures we found in school. Some of them are recognizable to what we saw in the prior study, but here we call them a fountain, a bottle filler, a tap, or a sprayer, which is usually attached to a sink. And we have estimated costs of replacing one of these, just material cost alone. So this analysis does not include labor and other abatement and so on. So here you can kind of see on the y-axis all the school districts that were in this 2022 data set. And on the x-axis, we have the material cost of replacing all the contaminated fixtures. I know it's a little hard to see because this is a very large graph, but I'll tell you the main takeaways. The most common and contaminated fixtures were fountains and taps. And a few districts here, I can show you, just material cost alone, all of these districts today could apply for at least a minimum of $12,000. And I would say maybe 4 times or more for including labor cost. So there's a lot of work to be done to communicate with districts and show them like you have ability to basically get free grant funding. So next we're kind of looking at the percentage of contaminated fixtures in a particular school plotted against the percentage of low-income students in that school. This y-axis data was from the OSPI report card data. Every year they publish for every single school a lot of demographic information about the students in that school. And so we collated that and used it. When you first look at this, you might think, you know, there's not really that strong of a relationship between lead contamination and income. The incomes are pretty widely distributed across all of the schools. Each dot represents a school. But what I want you to recognize is we can still use this information to highlight high priority, high risk schools. What I mean by that is let's look at this quadrant in the map. Every single one of these schools in the districts that are shown in the parentheses have more than 40% of their fixtures contaminated with lead, and more than 40% of the school's students are low income. So I would argue that this is a starting point to figure out how to allocate funding or to reach out to help them source funding for remediation. So spatially, if you're curious about where these schools are, we can see they're kind of in this educational service district in the eastern Washington, and also spread out a little bit in western Washington. Overall, though, in 2022, most of the public schools that were tested by the Department of Health had less than 20% of the fixtures contaminated by lead. As you can see, most of the figured dots are on the left side. And there's not a real clear conclusion or correlation between this, which suggests that maybe if socioeconomic status or income is not a predictor for lead contamination, that lead is quite ubiquitous and pervasive in places whether or not they're low income or not. So next steps for this research is identifying actually a new data set that we just received, looking at number of flights going over every single school in King County. And this is from small airports. So if you remember and paid attention to my slides with the history of lead phasing out, one of them said phasing out gasoline, automobile gasoline. We have still not phased out, or there are no laws restricting lead in small aircrafts. So SeaTac, all those big planes, they don't use leaded gasoline, but Renton, Auburn, all these smaller aircrafts, they use leaded gasoline. And so one thing we want to do is overlay our data set with water contamination data from the schools with lead contamination to see where children are exposed to lead in multiple ways, not just water, but also through air. We're applying for a pilot grant from the EDGE Center here at UW to interview the district officials and to develop a tool that can help them easily access funding. And in this, we're already in conversations and built partnerships with OSPI and DOH, who are really excited about this research. In addition, I have a few local nonprofit leaders that have reached out to me when I was describing this research saying, can you help us identify schools where we should prioritize spending our nonprofit money to install air and water filters? So another pathway to remediation that's outside of all this grant funding and the slow bureaucratic processes. So we're working on that. And I'll close the talk. Hopefully perfect. We have about 15 minutes. I'll close by advertising. I saw Daniela do this last week, so I decided to do it too. By advertising 2 different classes. I know a few of you might be students, but this winter I'm actually teaching usability studies, but that's not really related to this research. You can still take it if you're a master's student and want to take a night class from 6 to 10 p.m. on Tuesdays. But the thing I wanted to draw your attention to if you're a student is there's a directed research group. This is hosted by HCDE, but if you're a student in other departments, you're also welcome to apply to take it. And we're focused on this LCRI, lead and copper rule improvement that was just passed into law last month. We want to get ahead of it and study it. So it's called Rebuilding the Nation's Drinking Water Infrastructure. Where are the lead pipes and what comes next? So here we're really trying to look at the lead inventories that public water systems are submitting and try to understand, are there places where people are replacing lead pipes with PVC, which could itself cause issues in the long term? How can we make decisions to really protect and make our infrastructure more climate resilient? And in spring 2025, I'll be teaching a PhD seminar called Conducting Actionable Research to Promote Social and Environmental Sustainability, Translating Data into Impact. And this one's really focused on UN Sustainable Development Goals and how we can really understand our research through that lens. And now I have a picture of cherry blossoms, which will come up next quarter, and that's it. Thanks.